It's Saturday, December 7th, 2024. These are the solutions to the review questions for your final exam. The first question, we're supposing that 23% of stones on the beach are red in color. And so notice that this 23% is a population parameter. You plan to collect 200 stones selected at random and then to calculate p hat, the proportion of red stones in your sample. So first, the distribution of p hat will be approximately normal, provided certain conditions are satisfied. State each condition and briefly explain why it is satisfied in this scenario. And so what we're talking about is, under certain conditions, the distribution of p hat is approximately normal, centered at the population proportion, and with a standard deviation which is a function of that population proportion and of the sample size. And so it might look something like this. In class, I mentioned 4 conditions, but for the purpose of the exam, you only need to take into account 2 conditions. The first one is the independence condition. This condition is satisfied provided we have a random sample from the population. In this scenario, it's stated that we're going to take a random sample, so we're good. The sample size condition, when the population proportion is given, as it is in this case, then we just need to check that n times p and n times q are both at least 10. And so in this scenario, n times p is a sample size of 200 times a population proportion of 0.23. That gives us 46. So we expect, on average, in a sample of 200 stones, 46 will be red. And that leaves 154 that are not red. Both of these values are greater than 10, and so we're good. What is the mean and standard deviation of the sample proportion, p hat? Well, the mean is given. We were told that the mean value is 0.23. The sample size is 200, so we can use now the mean and the sample size to calculate our measure of uncertainty, the standard deviation. And so here the standard deviation, it's a simple calculation. It's p times q over sample size n, and we get 0.0298. Using the empirical rule, approximately 95% of sample proportions will be between what 2 values? Well, with the empirical rule, we know that 95% of observations will be within 2 standard deviations of the mean. So 2 standard deviations is 0.0596. The mean of the distribution is 0.23. And so we just need to take that number plus and minus 2 standard deviations, and we get 0.1704 and 0.2896. So what we're saying is, because the normal approximation is valid because of our conditions, the conditions hold, we can say that on average, 95% of the time when we get a p hat, it's going to be between 0.1704 and 0.2896. Calculate the probability that p hat will be less than 20%. So here, we're going to make use of what we know about the approximate distribution of p hat. We're going to standardize. We can make a sketch if we want to help us understand what's going on. The value we're looking for is the area in the lower tail of the standard normal distribution from our z-score to the left. So our z-score is minus 1.007. That comes from standardizing our value of interest, which was 0.20. And remember that the z table only emits z values up to 1 decimal place, up to 2 decimal places. And so we're looking here for minus 1.00, and that gives us 0.1587 as the area in the lower tail. And so we can say the probability that the sample proportion p hat will be less than 0.20 is 0.1587, or about 16%. And finally, how would this probability change if the sample size was increased to 300? So you're going to answer it will get bigger or it will get smaller, and then explain why. So here we tell you that that probability is going to get smaller. And let me show you why in pictures. So here on the left we have the distribution of p hat when the sample size is 200. So that distribution is centered at 0.23. And if we consider a value of interest 0.20, we want to know the probability p hat will be less than 0.20. Then we just find the area in the lower tail. So we standardized to get the distance in terms of standard deviation. So we got 1.007 to the left. And we found that the area in the lower tail was 0.1587. So if we increase the sample size from 200 to 300, that area in the lower tail is going to get smaller. In other words, the probability that p hat is less than 0.20 is going to get smaller. And why is that? It's because when you increase the sample size, the tails of the distribution move inwards. That's because with a larger sample size, the distribution is taller and narrower. So it might look something like this. Right? See? So on the right is the distribution of p hat when the sample size is now 300. And you can see the distribution is taller and it's less wide than before. And so the tails of the distribution moved inwards. And so using the same values, this distribution is still centered at 0.23, and the value of interest is still 0.20. But two things change. First of all, when you standardize, you see that the distance between 0.20 and 0.23 is now bigger than it was before. Why is it bigger? Because when you standardize, you divide by the standard deviation. A larger sample size gives a smaller standard deviation, which increases the z-score. And so by increasing the z-score, you can see also that the area in the lower tail is less than it was before. You can just visually see it. Now, I know that's a complicated explanation. And I just tell you this, for the final exam, you won't need to provide the explanation, but you might need to know the answer to the question E. And that's just the first part, and that is, would this probability change if the sample size was increased? And answer, it will get bigger or it will get smaller. You need to know that if you increase the sample size, that lower tail area is going to get smaller. Right? That's what you need to know. The explanation for why is not as important, but I provide you that just because it might help you remember. Moving on to the second question. Here we're talking linear regression and we're talking about babies. So the scatter plot we're about to look at shows the height of 50 girls in centimeters plotted against their ages being between 2 and 5 years. The line of best fit is shown in red. So what are the conditions that must be satisfied to justify the use of the simple linear regression model in this scenario? Name 5 conditions and state whether or not they are satisfied. Well, let's just review what those conditions are. First of all, your two random variables, x and y, that would be your predictor and your response. Or you might say your independent and dependent variables. They must be quantitative. Second, the scatter plot must exhibit a linear association. In other words, the linear enough condition must be satisfied. And the way we normally check that is we look at the residuals. Thirdly, the spread must be roughly constant. And what we're saying is the spread of the data values in the vertical direction must be roughly constant as you move from left to right. That's called the thickening of the plot condition. And we check that also by looking at the residuals. 4, there must be no evidence of a lurking variable and no evidence of outliers. So in other words, nothing unusual going on. And lastly, the residuals themselves must be consistent with a normal distribution. And we check that by looking at a normal probability plot. So let's just look at these in a little bit more detail. So here's an example where we have on the vertical axis the standardized residuals, on the horizontal axis fitted values. These data come from a different scenario, not the one we're looking at, but a different one. And you can see here that the spread in the vertical direction gets larger as you move from left to right. And so the thickening of the plot condition, again, states that if there is a thickening of the plot in the residuals, then the regression model is not appropriate. And so on the left, this is an example where, because the residuals look the way they do, we would say the regression model is not appropriate. Okay, now we're looking at another example. This, again, is a different set of data, not the one from the question we're looking at. And this set of data is illustrating the other condition that we call linear enough. So the linear enough condition states that if there is any linear or nonlinear trend in the residuals versus fits, then the regression model is not appropriate. So on the left here, you can see that there's clearly a nonlinear trend in those residuals. And so here again, this would be a case where the linear regression model would not be appropriate. So what would the residuals look like if the model was appropriate? Well, here's yet another example. Again, this is a different set of data. What can we see here? The spread in the vertical direction is roughly the same as we move from left to right, and there's no evidence of any kind of trend in the residuals. So here the regression model is appropriate because there's no thickening of the plot and there is no trend in the residuals. And so in other words, the thickening of the plot and the linear enough conditions are satisfied in this example. Now what about the normal condition? Well, on the right here you can see a normal probability plot. Now I want to emphasize that a normal probability plot has nothing to do with linear regression. All this kind of plot is used for is we take any data set, and if we ask, is the distribution of our sample data consistent with a normal distribution, that's what we use a normal probability plot to find out. And so how do we find out? We look at those blue markers. Each one corresponds to a data value. And if those blue markers are approximately in a straight line, then we can say that data is consistent with the normal distribution. So in this particular case, the data happens to be residuals. You can see on the horizontal axis, we're looking at residuals. And so in this particular case, the residuals from a linear regression, those residuals are consistent in their distribution to a normal distribution, and so that condition would be satisfied. This is what it would look like if that condition was satisfied. So going back to the original data, where we have the age of baby girls between 2 and 5 years and their height, we have that the predictor variable, which is age, and the response variable, which is height, these are both quantitative, and so that condition is satisfied. There's no obvious outlier, so that condition is satisfied. And clearly there's no evidence of a lurking variable, so no worries there. The scatter plot looks linear, and so you might be tempted to say the linear enough condition is satisfied. I think that would be okay. But normally we would show you the residuals. And as I showed you on previous slides, you need to make sure that in those residuals, there's no evidence of any kind of trend, linear or otherwise. So here we would need to look at a residual plot to be sure that this condition is satisfied. Likewise, the constant spread in the vertical direction, you can see that if you visualize the spread of the data cloud on the two sides of the regression line, above and below the regression line, that spread is roughly constant. So looking at this plot alone, we could say probably that condition is satisfied, but we can't tell for sure until we look at the residuals. So the constant spread, the thickening of the plot condition, we cannot tell without looking at residuals. And again, I emphasize, if you're given a question like this on the final, you will be shown a plot of the residuals. And are the residuals consistent with a normal distribution? Here, we're not shown a normal probability plot for the residuals. If we were shown a normal probability plot, we would just need to see that those markers are roughly in a straight line. If so, we would conclude that the residuals are approximately normal in distribution. Here, we can't tell that for sure because we don't have that plot. Provide an interpretation for the slope of the regression line in the context of this scenario. Well, here the slope, remember, is the number that goes in front of the predictor variable. In this case, the predictor is age in years. So the number in front of that is 10.50. And so what that tells us is for every extra year of age, we expect on average to see the height of the child to increase by 10.50 centimeters. Right, so the slope indicates that for every additional year of life, the height of a baby girl between 2 and 5 years of age is expected to increase by 10.5 centimeters on average. So that kind of answer gives you all of the context of the scenario. That's the kind of answer I'll be looking for on the final. Provide an interpretation of the intercept of the regression line in the context of this scenario. So just to remind you, the intercept is the number that's sort of sitting by itself. It's not multiplied by the predictor variable. It's sitting by itself. And so that's called the y-intercept. The height would be predicted to be that value if the age was 0. However, we cannot make that interpretation for a very good reason. So here, the intercept is 59.58 centimeters. It's the height when age is equal to 0. So that much is true. But it cannot be interpreted because the model applies to baby girls between 2 and 5 years of age only. And why is that? It's because this linear regression line was fitted to the data that only goes from 2 to 5 years of age. If we were to make predictions for years of age less than 2 or more than 5, that would be called extrapolation. And extrapolation is not correct. You're not supposed to extrapolate. Now, I'd like to remind you why extrapolation is a no-no. So here's the example that I used in class. So in this case, we imagine that we had data for the mass of a snake versus the height versus the length. We had data with masses between about 1.5 up until 2.5 kilograms. That was the data that was used to fit the regression line. So those vertical dashed lines show us the extent of the data that was used to fit the model. And so you can see within that range, between those dashed lines, the data looks linear. And so it's perfectly all right to fit a linear regression line. And it's also perfectly all right to make predictions for snakes whose mass is in that range between those dashed lines. If we were to make a prediction for snakes whose mass is outside of that range, say 3 kilograms or 5 kilograms, that would be incorrect. That would be called extrapolation, and that is incorrect. And the reason it's incorrect is because the only data we've seen is the data between 1.5 and 2.5 kilograms, the data between those dashed lines. That data looks linear, but we don't know if the linear trend extends beyond 2.5. And so in the example I used in class, I imagine that if we were to collect more data, we might see that the trend actually isn't linear. It starts to level out. And you can see how bad the predictions would be, especially for 5 kilograms. If we were to extrapolate using the model equation, 5 kilograms gives a prediction of 222 centimeters in length. And you can see that's very far from the actual observations. So extrapolation is not to be done. The coefficient of determination in this case, and this is our data for the babies, is 26.15%. What is the correlation between height and age for this data set? That's a very straightforward question. We just take the coefficient of determination, we write it as a decimal, and take its square root. That gives us a correlation. Provide an interpretation of the coefficient of determination in the context of this scenario. And so what that number says is that 26.15% of the variation in the response variable, height in centimeters, is explained by differences in the predictor variable, age in years. One girl who is 4 years of age is 89.65 centimeters in height. Use the model equation to calculate the fitted value and the residual for this person. Well, the fitted value is straightforward. We just write out the equation for that line of best fit, and we put 4 in place of age in years. During the calculation, we get our fitted value 101.58 centimeters. So the model is predicting that a child of 4 years of age will be 101.58 centimeters on average. To calculate the residual, we just take the difference between what was observed and what was calculated to be the fitted value. That difference, in this case, minus 11.93 centimeters, that's the residual. Draw a circle around the data point with the largest residual. So the data point with the largest residual is the one that is the furthest away from the line of best fit. And to my eye, it would be this data point here. That data point has the largest residual. It's the most distant away from the line of best fit. Right, so the data point that is farthest from the line of best fit has the largest residual. Are there any influential points in this data set? State yes or no, and then explain why you think so. And the explanation is basically you can state the definition of an influential point, and then state whether there is a datum that satisfies this definition. So let me first remind you what we mean by an influential point. And to do that, I need to first talk about leverage points. So here we have an example. On top is data that includes a leverage point. So that point right there is a leverage point. And why? Because it's far away from the rest of the data in the x direction. The data set below that, the graph below that, shows the same data with the leverage point removed. So this observation here is called a leverage point. It is potentially influential. So what do we mean by influential? Well, let's just observe a few things. First of all, the coefficient of determination for the top data set is 19%, and the line of best fit has a slope of 11 centimeters per kilogram. Now here, the thing that matters is if that data point is removed, what happens to the slope of the line of best fit? Well, removing that data point, first of all, it increases the coefficient of determination. And that makes sense because you see that leverage point has a very big residual. The distance between that leverage point and the line of best fit, that vertical distance, is very big. So by removing that data point, we're removing a data point with a big residual. That's going to make r squared larger. But more importantly, you can see by removing the leverage point, the slope has increased by quite a bit, more than 3 times. And so this leverage point is highly influential because its removal caused the slope to change by a lot. Right, so now we know an influential point is a leverage point that has an impact on the slope of the line of best fit. So to be influential, you must be a leverage point. Looking at this data, we can see that, in fact, there are no leverage points because there are no individual data points that are far away from the rest of the data in the x direction. So here, there are no influential points, and why? Only leverage points can be influential, but here, there are no leverage points. So next we look at the foundations of probability. And so you need to remember the 4 basic rules of probability. We have an addition rule for disjoint events, a multiplication rule for independent events, the complement rule, and also you need to remember that disjoint events are dependent events. So here we're looking at the color of cars in Halifax. We have a distribution, and we're asked what is the probability that one randomly selected car will be black or white. So the event that the car is black and the event that the car is white, these are disjoint events because they both cannot happen at the same time. We're drawing only one car, and it's either going to be black or white. And so the probability of black or white is just the sum of the probability of being black plus the probability of being white, 0.44. And that's the addition rule for disjoint events. If 3 cars are selected at random, what is the probability that none are red, and which rule applies in this case? Well, the probability of being red is 7%, so the probability that the car isn't red is 93%. And so that little calculation, technically, it makes use of the complement rule. However, the rule that really we use most in this case, the probability that no red in 3 draws is equal to the probability that the first car isn't red, which is 0.93, times the probability the second car isn't red, 0.93, times the probability the third car isn't red, 0.93 again. So it's basically just 0.93 to the power of 3, which is 0.8044. And so that calculation makes use of the multiplication rule for independent events. So we're assuming that the color of a randomly selected car, the first one versus the second one versus the third one, those 3 outcomes we're assuming are independent of each other. And so we're using the multiplication rule for independent events. If 3 cars are selected at random, what is the probability that at least one is red, and which rule applies? So when you see a question that contains the words at least one, that is a hint that you're going to use the complement rule. And here the reason we use the complement rule is because the probability that at least one car is red is not easy to calculate directly, but the probability of the complement that none are red is easy to calculate, right? So we know that the probability of being red is 7%. The probability that none are red is the number we just calculated. So the probability that at least one is red is 1 minus 0.8044, 0.1956. This makes use of the complement rule. If 3 cars are selected at random, what is the probability that all 3 are red, and which rule applies in this case? Well, again, the probability that a car is red is 7%. So the first car has a 0.07 probability of being red. The second car, 0.07 probability, and the third car, the same. So the probability that you get 3 red cars is just 0.07 to the power of 3, 0.0003. And so that, again, makes use of the multiplication rule for independent events. Next question is involving the sum or difference of 2 random variables. So here, Iskandra, we imagine, runs a dairy farm. Her cows produce an average of 45 liters of milk per day with a standard deviation of 8 liters. Iskandra's neighbor also runs a dairy farm. His cows produce an average of 60 liters of milk per day with a standard deviation of 10 liters. And so for the purpose of this scenario, let x1 represent the quantity of milk produced by Iskandra's cows on any randomly selected day, and x2 represent the quantity produced by her neighbor's cows on any other randomly selected day. Let us assume that the random variables x1 and x2 are independent and normal in distribution. So first calculate the mean and standard deviation of y equals x1 minus x2, the difference between the quantity of milk produced by Iskandra's cows and the quantity produced by her neighbor's cows. So we're given the parameters of each distribution. For Iskandra, mean is 45, standard deviation is 8. For the neighbor, the mean is 60, standard deviation of 10. So what are the mean and expectation of the difference between these two values? Well, the expectation is just the difference between expectations, minus 15 liters. So what this is saying is that the neighbor's cows produce 15 liters more on average compared to Iskandra's cows. To get the standard deviation, we first must calculate the variance of this random variable y. So the variance is just the sum of the variances. And so you need to remember that variance is standard deviation squared. So we have 8 squared plus 10 squared. To go back to standard deviation, we take that variance and we calculate its square root. So the square root of 164, we get 12.8062 liters to be the standard deviation of our random variable y, which is the difference between x1 and x2. So we can say y follows a normal distribution with a mean of minus 15 liters and a standard deviation of just about 13 liters. What is the probability that y is greater than 0? Or in other words, what is the probability that Iskandra's cows, if you take one selected at random produce more milk than her neighbor's cow if you take one selected at random. So what do? We standardize the value of interest. In this case, the value of interest happens to be 0. And so it's 0 minus the mean divided by the standard deviation. That gives us 1.17. So to draw a picture, here we have the distribution of y, centered at minus 15 liters, and the value of interest is 0 liters. What's the distance between minus 15 and 0 liters in this scenario? It's 1.17. In other words, 0 is 1.17 standard deviations to the right of the mean value. And so to get the probability we're looking for, we just need to find the area to the right of 0, the area in the upper tail. So now, to do that, we need to look at the z-table. We look up our standardized value, our z-score, or in other words, our test statistic, 1.17. And we see that the area to the left of 1.17 is 0.8790. So the area to the right is 1 minus that, 0.1210. Right, so the probability that one randomly selected cow from Iskandra's herd of cows produces more milk on any given day compared to one randomly selected cow from her neighbor's herd, that probability is about 12%. Next question. Iskandra owns an apple orchard. To assess the quality of her product, she randomly selected 50 apples and found that 37 were sweet and the rest were sour. So here we're going to construct a 95% confidence interval for the proportion of all her apples that are sweet. And I go by following these steps. Well, the steps are here. So first we're going to collect our data. So we have 37 sweet apples out of a sample size of 50. We're going to make a 95% confidence interval. And what we need to do in the end is to calculate a point estimate plus or minus a margin of error, that margin of error being the product of a critical value and a standard error. So we need to calculate p hat and also the standard error of p hat. So calculating, p hat is just 37 over 50, that's 0.74. The standard error is a function of that value and also of the sample size. That turns out to be 0.0620. And so the margin of error, it's the critical value times the standard error. The critical value for 95% is 1.96. The standard error, we calculate it. And so we get a margin of error of 0.1215. So now we can calculate our upper and lower bounds. It's p hat plus or minus the margin of error, which gives us 0.6185 and 0.8615. The interpretation of the interval, we just say that assuming the conditions for the normal approximation are satisfied, we are 95% confident that the proportion of Iskandra's population of apples, that is, all the apples in her orchard that are sweet, is between 61.85% and 86.15%. Now notice 0 is not in this interval. However, in this context, that doesn't really matter because we're not really asked whether or not any of our apples are sweet. We're just asked to get an interval estimate of the proportion that are sweet. So 0 in this case has no significance. And maybe I should say further that the fact that 0 is not in this interval, in this scenario, has no significance. Suppose we want to estimate the proportion of Iskandra's apples that are sweet using a 99% confidence interval with a margin of error of no more than 2%. What sample size is required? So let's remind ourselves that for a 99% confidence interval, the critical value is 2.576. This is our formula for calculating a sample size required to obtain a certain margin of error for a given level of confidence. So we plug those values in. The critical value for that level of confidence, 99%, is 2.576. The margin of error is 2%, so we put in 0.02. And now for p-guess, since we have data from the previous part of the question, we have already a good estimate of the true proportion of apples that are sweet. That's 0.74. So we're going to plug that into the formula, and we get a sample size of 3,192 after rounding upwards. And so just like to point out, by the way, that the sample size is really big. And imagine collecting that many apples and determining whether or not they're sweet. That's a lot of bites of a lot of apples. But the reason the sample size is so big is because a margin of error of only 2% is very small. So Skander's neighbor grows apples as well. He claims that 92% of his apples are sweet. Iskandra plans to secretly conduct a hypothesis test to see whether the true proportion of her neighbor's apples that are sweet is less than what he claims. She will conduct the test at the 5% level of significance. So what are Iskandra's null and alternative hypotheses? And what is the probability that Iskandra will falsely conclude that the true proportion is less than 92%? Well, here it's 92% of Iskandra's neighbor's apples are sweet versus less than 92% are sweet. So the null is that that proportion is equal to 92%, or 0.92. The alternative is that it's something less. If the null hypothesis is true, then the probability of falsely rejecting it, in other words, of making a type 1 error, is equal to the level of significance of the test, which in this case is 5% or 0.05. So Iskandra plans to purchase a random sample of n apples from her neighbor. What is the minimum sample size required to satisfy the success-failure condition in this scenario? So the success-failure condition, also called the sample size condition, states that the sample size must be large enough so that we can expect to see at least 10 successes and at least 10 failures. So we're assuming the true proportion under the null, 0.92. So we need that both sample size n times 0.92, that's the expected number of sweet apples in the sample, and n times 0.08, the expected number of sour apples, both of these must be at least 10. The trick is to divide 10 by the smallest proportion. Rather, I should say the smaller proportion. And so in this case, the smaller proportion is 0.08. So 10 divided by 0.08 gives us a sample size of 125. So the minimum sample size in order to satisfy the success-failure condition is 125 apples. So suppose Iskandra plans to take a bigger sample. She's going to take 150 randomly selected apples from her neighbor. What is the standard deviation for p hat? So assuming the null is true, the standard deviation for p hat is just 0.92 times 1 minus 0.92 divided by the sample size and then take a square root. Turns out to be 0.0222. Now suppose we have some data. 142 of the 150 apples that Iskandra purchased were sweet. We're going to calculate a z-score and a p-value. So remembering the null hypothesis gives the mean, and we just calculated the standard deviation. That allows us to standardize p hat. So p hat itself is 0.9467. And then standardizing, we take p hat minus the mean divided by the standard deviation. We get 1.20 standard deviations. So we're going to provide a conclusion. Here, just to remind you what the decision rule is, we're looking for critical value which puts 5% into the lower tail because it's a 5% test. That critical value is minus 1.645 standard deviations. So the rejection region is to the left of that number. We don't reject if our test statistic is to the right. The decision rule is we will reject the null hypothesis if the test statistic, that is the z-score, is less than minus 1.645. And here, our test statistic is way over to the right of our critical value, 1.20. So clearly, we cannot reject the null hypothesis. So the conclusion is we cannot reject the null at the 5% level of significance. There is no evidence that the proportion of Iskander's neighbors' apples that are sweet is less than 92%. Now, this question did ask to calculate the p-value. It actually doesn't make much sense to calculate the p-value in this scenario because you can see that the test statistic is so far to the right that the p-value is going to be a very big number, and I don't even care what it is. So I'm just going to leave that one in this case. Next question. In the year 2020, Sockway purchased 112 pizzas from Pizza Be Good, 85 of which were yummy. In 2021, Pizza Be Good hired a new chef with the aim of improving their product. During this same year, Sockway purchased 115 pizzas, 92 of which were yummy. Construct a 95% confidence interval for the difference between the probability that a pizza will be yummy under the old chef from 2020 compared to the probability that a pizza will be yummy under the new chef in 2021. So first, what are the conditions that must be satisfied to justify the use of the normal model in this scenario? And are they satisfied? For the purpose of the final, we have two conditions that we need to consider. First of all, there's the independence. The independence assumption is satisfied because we can assume that the samples from each year are a random selection of pizzas made that year. And also, the two samples themselves are independent of each other because there was one chef in 2020 and a different chef in 2021. The second assumption is to do with the sample size. So this is what I often call the success-failure condition. Under this assumption, there must be at least 10 successes and at least 10 failures in both samples. And so here that is the case because in the first sample we have 112 pizzas, 85 of which were yummy and 112 minus 85 of which were not yummy. Both of those numbers are at least 10, and so we're good with that sample. And likewise, in the sample from 2021, 92 successes out of 115 pizzas. So that gives us at least 10 successes and at least 10 failures as well. So the sample size assumption is also satisfied. Calculate the sample proportions, P1 hat and P2 hat, and their difference. So looking at the data, it's very straightforward to calculate P1 hat, 85 over 112. P2 hat is 92 over 115. And the difference between them, minus 0.0411. So this difference, P1 hat minus P2 hat, is a point estimate. It's our best estimate for the true difference, P1 minus P2. Calculate the standard error for the difference, P1 hat minus P2 hat. Right, so here we want to take into account the uncertainty, and we measure uncertainty in the case of a confidence interval with standard error. And we just need to remember how to plug our numbers in. So we have two fractions under the square root sign. In the first case, we're looking at P1 hat times 1 minus P1 hat divided by sample size, and then plus P2 hat times 1 minus P2 hat divided by sample size. So looking at that calculation, let me go back for a second. So for the purpose of your final, with a question like this, I want to see exactly what you're seeing here, with the appropriate numbers in place, of course. So I want to see you write out how you would calculate the standard error. And then if you want to do the calculation in one step on your calculator using the memory function, that's okay. So the next thing you would just write down is the final answer. But you can also do it in steps if you wish, if you don't want to use the memory function or if you don't know how. and that's okay too. In the end, in this case, you should get 0.0550 as the standard error. Next, we'll calculate the margin of error. And so just a reminder, that margin of error is the product of the critical value times the standard error. The critical value, of course, comes from a table. You're going to have a table written on your formula sheet. In this case, it's a 95% interval, and so the critical value is 1.96. And so the margin of error is 1.96 times 0.055. And finally, we're going to calculate the upper and lower bounds of our interval and provide a conclusion based on what we see. So, the confidence interval is the point estimate plus or minus the margin of error. And in this case, we get an interval that starts at minus 0.1489 and ends at 0.0667. The critical thing here is that the interval contains that very special number, 0. 0 is in the interval. And so what that tells us is we have no evidence from this data that the true values, P1 and P2, are any different from each other. In other words, 0 is a plausible value for P1 minus P2. And so we make two conclusions. First, assuming the conditions for the normal approximation hold, we are 95% confident that the difference in the population proportion of yummy pizzas made at Pizza Be Good in 2020 compared to 2021 is between minus 14.89% and plus 6.67%. Furthermore, since 0 is in the interval, there is no evidence that the two population proportions are different at the 95% level of confidence. Next question. This is the one where we have cats and dogs. So we're pretending that we interviewed 127 randomly selected dog owners and said, is your dog a good dog? 102 of those owners said yes. And then we selected 233 cat owners at random and asked them, is your cat a good cat? 173 said yes. And so here we're going to conduct a hypothesis test to see whether there's evidence that the proportion of dog owners with a good dog is any different than the proportion of cat owners with a good cat, and we're testing at the 1% level of significance. So first, the hypotheses. P1 will be the proportion of dog owners with a good dog. P2 will be the proportion of cat owners with a good cat. And the null is that those two proportions are equal to each other. And since we're just looking to see whether they're different, we're going to use the two-tailed alternative hypothesis. Next, we do the calculations. We need our proportions and the difference between them. So those proportions are very straightforward to calculate. The difference between them, 0.0606. So what this represents is a point estimate, and it's our best estimate of the difference between the two proportions, P1 and P2. But of course, our point estimate is not enough. We need to take into account uncertainty. And so we move on to calculate the standard error. To do so in this scenario, we first have to calculate this pooled proportion. And just to review again the reason why we use it, we remember that when we do a hypothesis test, we start with the assumption that the null hypothesis is true. And so under the null, P1 and P2 are equal. So it's as if we have two samples from one population with the same proportion. And so that justifies pooling the data to calculate our best estimate of that common proportion. And so that estimate here is 0.7639. And so now we're ready to calculate the pooled standard error using that pooled proportion. And so plugging that in, we get P pooled times 1 minus P pooled over 127, that's the number of dogs, and then plus P pooled times 1 minus P pooled divided by 233, the number of cats in our sample. When it comes to doing this calculation, again, I remind you that on the final, I want to see what you have written here. After that, if you want to write the final answer of this calculation, you can do so. And that would be for those of you who intend to use the memory function on your calculator to make the calculation a little bit easier. But you don't have to do it that way. You can also do it in steps. So if you were to do it in steps, you would calculate each of these fractions, then add them together, and then take a square root. Now here I want to review just one more time what to do about scientific notation, because if you're going to do the calculation step by step, you may have to deal with scientific notation. So let me just show you that again. So here, the first fraction, actually, in the first fraction, we don't need to worry about scientific notation, because as you see, the first digit that appears is in the third decimal place. So let me show you what I mean. If we go 0.7639 times 1 minus that number, 0.2361, and divide by the sample size, you see we get a decimal number where the first digit is in the third decimal place. And so usually calculators won't give you scientific notation for a number like this. So we can just write out 0.0014, no problem. Now in the second case, you can see from the answer I have here, the first digit actually appears in the fourth decimal place. And so that's usually when you get scientific notation. So just doing this calculation again to show you, 0.7639 times 0.2361, whoops, divided by 233. So you see we get a number with scientific notation. So we have that -4 at the end. So that -4 tells us that the first digit, in this case the first digit is a 7, that first digit goes in the fourth decimal place. Now, not so fast. The second digit is also a 7, and so we have to round up. And so we're going to round that first digit to an 8, and then we write 0.0008. So notice that 8 is in the fourth decimal place. If you take that decimal, you got 3 zeros from the decimal, and then the 8, it's in the fourth decimal place. So that's how you deal with the scientific notation. So in any case, doing the calculation in the end, you get a pooled standard error of 0.0469. And so next we're going to calculate our test statistic and then a p-value. So again, the test statistic in the case of a comparison between two sample proportions, we have an observed difference minus the difference under the null, which for our purposes is always going to be 0, and then divide by our measure of uncertainty, the pooled standard error. And so we have the point estimate, and we have our pooled standard error, so now we can go ahead and do that calculation, and we get a test statistic, or in other words, a z-score of 1.29. So before we calculate our p-value, let's just look at our decision rule. So here I'm asking for a conclusion already, so that's fine. 1% level of significance. Let's look at that decision rule. Here's our normal distribution. This is a standard normal distribution. It's a distribution of our test statistic, or z-score. We need two boundaries that put 0.5% into each tail, right? Because it's a two-tailed test, we're going to take that level of significance, that alpha, and divide it equally into the two tails. So we're going to put 0.5% into each tail. Looking at our table of critical values, which you will have on your formula sheet, you can see that for to put 0.5% into each tail, we need to use the critical value for 99% confidence interval. Right? In other words, between these two critical values, these two boundaries that I marked, we're going to put 99%, and so that's why we use plus or minus 2.576. Just to sort of review the concept, supposing we were testing at the 2% level of significance, and it's a two-tail test, then we would have used plus or minus 2.33, because that puts 1% into each tail. Okay, so in any case, our rejection region marked in red here, we're going to reject the null hypothesis if our test statistic falls into the red. If it's anywhere else, we're not going to reject. And in this case, our test statistic is 1.29. Clearly, that's not in the rejection region. And so conclusion is we cannot reject the null at the 1% level of significance. There is no evidence that the proportion of dog owners with a good dog is different than the proportion of cat owners with a good cat. So that's our conclusion. Let's go back now and calculate the p-value. So to do so, of course, we need to use our z-table. We need to look up our test statistic. And now here, the thing to remember, because it's a two-tailed test, we need to not look just the area from 1.29 to the right. We also need the area from minus 1.29 to the left. Now, of course, those two areas are the same because of symmetry. To look up the value we need, it's convenient to use the negative number, because then we don't have to go 1 minus whatever proportion we get. So looking up the area to the left of minus 1.29, we can see that area is 0.0985. And so the p-value is twice that number. The p-value is 0.1970. And since this number is greater than 10%, we conclude that there is no evidence to support the alternative hypothesis. And what I'm talking about there is using these adjectives for the strength of the evidence in support of the alternative hypothesis. Here, the p-value is bigger than 10%, and so we can say there's no evidence in support of the alternative. Next question is a relatively easy one. Here we're looking at a contingency table. In this case, we have children who were randomly selected from 3 different countries. That's one of our categorical variables. The other category would be the number of hours they play Xbox per week. So we have 0 to 5 hours per week, 6 to 10, and 11 or more. So remember, when you're dealing with the contingency table and you're asked to calculate a probability or proportion, we have to ask ourselves 2 questions. First, who are we talking about? That number goes on the bottom. And what is the contingency or condition? That goes on the top. So in the first case, we're asked what percent of all the children surveyed were from Canada and played 0 to 5 hours per week. So here we're talking about all children, and so that would be 317. And the contingency is we're looking for children from Canada who played 0 to 5 hours per week. That's 19, and so the answer is 19 over 317, which turns out to be 0.0599. In the next example, among the children from Canada, what percent played 0 to 5 hours per week? So we're talking about the children from Canada. That's the who. The condition now is they played 0 to 5 hours per week. And so the who is 118. And the condition is they played 0 to 5 hours per week. So that's 19 out of 118. And so that turns out to be 0.16110. And the last one, among children who played 0 to 5 hours per week, what percent were from Canada? And so here the who are the children who played 0 to 5 hours per week. That's 170. And of those, the ones from Canada, 19. And so the ratio is 19 over 170, 0.118. Okay, so I'd like to finish off our review for the exam by just going over the way a box plot is constructed. And so here you recall that we were way back, we were looking at data where we were imagining we had 30 measurements of the length of a grass snake in centimeters. And so using this data and then constructing the box plots, let's just go through that. So when you construct a box plot, let's suppose you had to do it by hand. You will never will have to do this, but let's imagine what the computer does. Let's put it that way. First thing the computer needs to do is to calculate a scale for the box plot. So we do that. We can see we have numbers between 100 and 700 in our data. And so our scale goes from 100 to 700. We then want to look at the 5-number summary, and we're going to mark the median and the first and third quartiles. Right, so the red line is the median, 224 on the bottom, that is Q1, the first quartile, 375 is the third quartile. So we mark those in, and then we draw a box. So that's where the word box plot comes from, is we have a box. And we know that that box contains or represents 50% of the data. Next, we have to calculate fences. And so the fences are calculated as follows. The upper fence is the third quartile plus 1.5 times the interquartile range. And what is that interquartile range? It's the height of the box. It's the difference between Q3 and Q1. So in this case, you can see it's 151. And so the upper fence, Q3 plus 1.5 times the IQR, that gives us 601 centimeters, 601.5 centimeters. The lower fence is similarly calculated. You start now at Q1 and you subtract 1.5 times the IQR. And so that puts us at minus 2.5. Now in this particular case, because the data represents the length of a snake, we know that the length can never be less than 0. And so we're going to put the lower fence at 0. Right, so what's next? Now we want to mark in the whiskers. And so the whiskers are going to be the biggest and smallest value in the data set that don't go outside those fences. And so for the upper whisker, you can see that the biggest data value in this data set is 610. But that's above the upper fence, so we're not going to count that one. The biggest value that is inside the upper fence is the 459. And likewise, the smallest value that is inside the lower fence is the 151. So that gives us the whiskers, so we draw those in. And typically, the fences are not indicated when you draw the box plot. Let's see, did I forget something? Oh yes, yeah, one other thing. So why do we draw those fences in the first place? Well, we can use them to determine whether we have any outliers in our data. So outliers are points that are outside of the two fences. In this case, there's no small number outliers. There's no numbers below 0. But we have one big number outlier. We have 610 centimeters, which is above that upper fence. And so we're going to mark that as an outlier. And so this is what the box and whisker plot will look like in the end. And so just reviewing the components of it, the box indicates the middle 50% of the data. The height of the box is the interquartile range. The line inside the box, that red line, indicates the median. And if the median is in the center, then the middle 50% of the data is approximately symmetric. If that's not the case, then the data is skewed. Skewness is also indicated when one of the whiskers is much longer than the other, which is not the case here. But here's a couple of examples I remember showing way back. The first example is showing a skew towards smaller values. So you see the tail, the lower tail, is stretching. It's much longer than the upper tail, so there's a skew towards smaller values. The opposite of that would be a skew toward larger values. So an asymmetry in the box plot or in the whiskers indicates asymmetry in the data. And finally, potential outliers are indicated individually. This emphasizes their potential importance in the analysis. So that takes us to the end of the review for our final exam. I hope you found all this very helpful. I look forward to seeing you on the day. That'll be right. I'll see you then. Bye.